Hi, welcome to this quick video. In this quick video, I'm actually going to talk about pH sensors. I was about to hold one up, but I realized I'm actually going to hold up a sheet of pH sensors. So I'm holding up a sheet of pH sensors here, and this is sort of to give you a sense of the scale of manufacturing that we are actually able to achieve with this kind of technology. So you can see that I've got a sheet of the pH sensors here. And with that said, let me dive back into the video itself. So I'm going to talk about the analysis of pH sensors as a function of time. So at Zimmer People, we have a very scalable way of making a continuous monitoring pH sensor, and they are available on our web store. On our web store, if you buy the technology, it's only ZP won't just support every application. They'll get you to technology readiness level number 3 potentially, so that you can just prove out some idea. But if you want to go kind of have ZP support you more in depth, then that's definitely a program. So at ZP, we on the website, we do have a data sheet for it. So we do show that, for example, here on the data sheet, we've tested at 2, 4, 6, 8, and 10. Because this is a sort of a classical pH sensor, here we're not showing the signal in terms of pH, but we're showing it in terms of millivolts or voltage. Now, on the website, on the data sheet, we show data over a course of like 400 seconds. But we do actually have some data, for example, about 62,000 seconds, which is approximately 16 hours. Now, what we have at Zimmer People is a complete technology stack. So we have, and our business model is contract development, contract manufacturing. So if somebody has the idea that they actually want to go to quite a high technology readiness level, if not TRL 9, then we look to people to engage with ZP so that we can kind of help take the technology to a TRL 9 in that particular application. Anyway, that said, we do have some longer data, and for example, this is 16 hours. We do have something called Julie real time, which means that we can analyze data and set calibrations remotely back onto a system in real time. Anyway, what I've done here is we've got some data, and I've basically chosen a calibration point here, and I've calibrated the sensor. So when I go here now, what we've added here is a secondary axis, which shows that having chose that calibration point at 1000 seconds, we have then just kind of applied that calibration to the entire data set. So rather than showing on the left hand side millivolts, so you can see that the millivolts over this 16 hours has gone from about 0.3 to something like 0.24. Now we've actually got pH going from pH 7, because that was my original calibration, to about 7.8. So over 16 hours, you could argue that we've had less than a 1 pH shift. But we do understand that, for lots of applications, they want tighter control. They don't want this, drift, let's say. So what I've done now is I've just sort of demonstrated to you how, without really much optimization, just kind of looking at the data, I've introduced a calibration point at 8,000 seconds, so 7,000 seconds later, and that's approximately sort of 2 hours later. I've introduced a calibration point. So now, this essentially drifting up. It was going from about 7 to less than 7.4. But we introduced that extra calibration, so we brought it back to 7, and so the axis slightly narrowed in, by the way. And then 2 hours later, we introduced another calibration, but you can see that by introducing that calibration there, we've basically, rather than it just drifting up, we kind of reset the calibration, and then we've reset the calibration again 2 hours later. So again, we've kind of rather than just letting it drift up, now we've brought it back to 7, and we did it again. At which point now we're starting to realize that actually you can see in the raw data that in fact, these sensors kind of equilibrate, and that's sort of understandable. You're kind of leaving it in the system. It generally is equilibrating. Most of the change actually happens earlier on, so you can kind of see that by about a third of the time through this 16 hours, we've more or less formed an equilibrium at this point, and at which point then we don't bother to calibrate again. So for the kind of last 5,000 seconds, which is 5,000 seconds is approximately about more than 4 hours. It's about 8 hours actually. We don't bother calibrating again, and you can see that at this point now that the sensor is, you know, sort of linear, is staying fairly constant, and then that means that the pH changes that we're actually looking at, we've really zoomed in here, is about 6.97 to just about 7.11. So at which point now we didn't bother to kind of calibrate again. So if I was to summarize this says that we have, if I was to summarize, we have a very low cost way of producing pH sensors, very scalable. This is a whole array, by the way, or a sheet of them rather. You just cut out the, do not cut out. We remove individual sensors. We've got 16 hours worth of data. You can see that most of the sort of equilibration is taking place earlier on, and then at about the 3,000 second time point here, it's equilibrated, and we didn't bother to we didn't rather need to calibrate again. If you do have any questions about our pH sensors, we'll link underneath this video, and also link to the product as well. As I say, if you're interested in just doing this yourself, then you can purchase this off the web stores. But if you genuinely want ZP to be engaged in development, then you have to engage us, or rather please engage us on a program. Okay, thanks very much.